Have you ever stopped to think about how your computer is even possible? I mean, how all those different apps and windows you have open can work together, almost like they're having a conversation? Well, today, we're going to pull back the curtain on those hidden conversations happening inside your machine. I want you to think about something you do every day, copying and pasting. You highlight text in your browser and then boom, it appears in your word processor. But those are two totally separate programs. How does that information get from one to the other? Well, it's not magic. It's a really cool and carefully designed system called Inter-Process Communication, or IPC, and we're about to break down exactly how it all works. All right, so before we get into the how, we got to ask a more basic question, why? Why do programs even need to talk to each other in the first place? Turns out, pretty much everything you do on a computer relies on teamwork. So, in the lingo of operating systems, any program you're running, your browser, your music player, anything, is called a process. Now, some of these processes are lone wolves, they do their thing and don't bother anyone, but most of them are cooperating, which just means their actions can affect or be affected by other processes. And this idea of cooperation, it's everything in modern computing. And why is this so critical? Well, first off, speed. If your computer has multiple processor cores, you can split a really hard job up between them and get it done way faster. It also lets developers build apps in a modular way, kind of like using Legos to build a big project from smaller, specialized pieces. And of course, it's the absolute bedrock of the internet itself, right? Your browser is a client that needs to talk to a web server somewhere else. That's cooperation. So, all of this amazing teamwork is made possible by inter-process communication. The best way to think about IPC is as the official rulebook, handed down by the operating system that lays out exactly how these different programs are allowed to pass notes, share data, and basically get things done together. Okay, so there are a couple of different ways programs can follow these rules. Let's start with a really simple, intuitive one. Imagine you and a friend need to work on a problem together. What's a really easy way to share ideas? You could just use a public whiteboard, right? And that's exactly what our first method is. In computer speak, that whiteboard is called shared memory. Basically, the operating system finds a chunk of RAM and says, okay, this area right here, you and you and you all have access to it. It's like giving multiple programs a key to the same room so they can all work on the same project. This diagram shows it perfectly. See how Process 1 and Process 2 are their own separate things? But the kernel, that's the heart of the operating system, creates this shared space in between them. Now, Process 1 can write some data into that space, and because Process 2 also has access, it can instantly read that exact same data. It's super direct and incredibly fast. So the whole flow here is really logical. First, one process has to ask the operating system to create this shared space. Then, any other program that wants to join the party has to attach itself to it. Once they're both looking at the same whiteboard, it's a free-for-all. One program writes, the other reads. Simple as that. Okay, but how does a program actually do that? It's not like it can just say, hey, operating system, give me some memory. Well, it kind of does, but it uses a very specific set of commands, or functions, to make these requests. The first command in the toolkit is usually something called shmumget. You can probably guess this one. Shmum for shared memory and get. A program uses this to tell the OS, hey, either create a brand new whiteboard for me, or if one with this name already exists, just tell me where it is. Right, so once the program knows where the whiteboard is, it uses shmat. The at here stands for attach. This is the command that actually links that shared space into the program's own world, its own address space, so it can finally start reading and writing to it. Now, this public whiteboard method sounds perfect, right? It's blazing fast, it's direct, but there's a catch. There's always a catch. What do you think happens if two people try to write on the exact same spot on the whiteboard at the exact same time? Yeah, you get a mess. Total chaos. One program might be halfway through writing something, and the other one just scribbles right over it. You end up with corrupted, completely useless data. And that is the big challenge with shared memory. The programs themselves have to figure out a way to coordinate and take turns. That whole process of taking turns is called synchronization. So if the public whiteboard can be a little too chaotic, what's a more orderly, more structured way to communicate? Well, how about a postal service? You write a letter, you put it in a mailbox, and you trust the mail carrier to deliver it safely. No one can mess with it while it's on its way. And that brings us to our second IPC method, message passing. With this approach, Programs don't share a common space at all. Instead, they communicate by sending tidy, individual messages to each other. And the key difference here is that the operating system kernel acts as the post office, managing the entire delivery to make sure nothing gets lost or scrambled. Just look at this diagram. The kernel is the official middleman. Process 1 doesn't talk directly to Process 2. It wraps its data up in a message and sends it to the kernel. Then the kernel holds onto that message safely in a queue until Process 2 is ready and says, "Hey, anything for me?" and receives it. It's this indirect path that makes it so robust. And the flow is just as orderly as you'd imagine. First, the sender creates what's called a message queue, which you can think of as its own private PO box. Then it starts adding messages to that box. At some point later, the receiver comes along and pulls the messages out one by one. It's a very predictable first in, first out kind of system. And just like with shared memory, there's a whole set of commands for this. You've got msgget to create the mailbox, mssend to send a letter, msrcv to receive one, and even msgctl to manage the whole thing. The operating system takes care of all the tricky stuff for you. All right, so we've looked at two totally different strategies for programs to talk to each other. We have the wide open public whiteboard of shared memory, and we have the formal, structured postal service of message passing. They both accomplish the same goal, but they're built for very different needs. This table here really lays out the trade-offs. When it comes to pure speed, shared memory is the clear winner. That direct connection is just hard to beat. But that speed comes at the cost of complexity. The programmer has to deal with that tricky synchronization stuff. Message passing, on the other hand, is way simpler to use because the kernel handles all that for you. But having that middleman adds a little overhead, which makes it a bit slower. And really, that's the bottom line. It all boils down to a classic engineering trade-off. Do you want speed, or do you want safety and simplicity? There is no single best answer. If you need every last drop of performance, you might choose the headache of shared memory. But if you value safety and ease of use, the slightly slower message passing is a no-brainer. Which brings us all the way back to where we started, that simple little action of copying and pasting. Now that you know the options, given that you want it to be fast and responsive, but it also absolutely cannot fail, which method do you think your computer is using right now? It's something to think about.